All right. Hello, everyone. My name is Danny Shaw. Welcome to the UW-Platteville Engineering Seminar Series. Uh, EMS seminars are 1 hour long presentation of real-world projects that showcase the plan, design, construction, maintenance of engineering projects and how they change our community. Attendees are also eligible to earn 1 professional development hours. All seminars are free and open to the public. To minimize the background noise, please, all attendees, please mute during the presentation. You're welcome to type your questions in the chat box during the presentation. At the end of the presentation, we will have a question and answer sessions, and then you are free to unmute yourself and ask questions. All right, today we are very excited to have Dr. Adam Dempsey coming from Marquette University. He planned to come here in person, but however, the weather didn't cooperate. So we'll change this into hybrid mode, have Adam to present through Zoom. But anyway, we're very happy you are here, both speakers and attendees. So I will give a very brief introduction for our speaker. Dr. Adam Dempsey is an assistant professor at Marquette University in the mechanical engineering department. Prior to joining Marquette, he was a senior research engineer at Caterpillar Incorporated and a postdoc researcher at Oak Ridge National Laboratory. Dr. Dempsey received his bachelor and master in mechanical engineering from Brandon University and his PhD in mechanical engineering from the University of Wisconsin-Madison in 2013. So please, everyone, help me welcome Dr. Dempsey. Right, Adam, it's all yours.
Okay, thanks, Danny, for the introduction. I really appreciate it. And I apologize again for not being able to make it today. That would have been great to meet everybody in person, but thanks again for having me virtually, and hopefully this is informative. So I'm going to talk about a new concept that we're working on that we feel can enable a fuel flexible mixing controlled combustion system for heavy duty engines using low carbon alternative fuels. So Danny did a great job introducing me, so I think I can probably skip my next slide. Let's see if I can actually get it to go to the next slide. There we go. I can get my laser pointer, which might be helpful. But yeah, my background, I have my bachelor's and my master's and my PhD in mechanical engineering. I did a postdoc at Oak Ridge National Lab for several years. And then I also worked at Caterpillar, which we were talking about is down in Peoria, Illinois, and I did combustion research there. And then I joined the faculty at Marquette University in August of 2019, just about 6 months before the pandemic started. So I did have some teaching experience with no mask on, but not any sense. And we're building a combustion research program at Marquette. So I'm going to talk a lot about engine research today, but we also have a rapid compression machine, which is more of a fundamental combustion research facility. So if you're interested in those types of topics, we have some activities in that space as well. For those of you who are not familiar, I was going to drive over to Platteville today from the other side of the state. So Marquette is located in Milwaukee, Wisconsin, just basically directly east of Platteville all the way until you hit Lake Michigan. Back in 2011, well before I joined Marquette, they did build a new engineering hall, which is pictured here. So we're doing our engine research in this sort of newer building, which is a 5-story building, and it's mainly faculty offices, machine shop, some classrooms, and then a lot of laboratory space. So most of our engineering research is done in this building. We still have the old engineering building, which is mainly classrooms. And just to give you a sense for how much engineering is growing at Marquette, we sort of spilled into this new 5-story building. So both buildings are still active. And the reason that we needed the new building is that Marquette has goals of really aspiring to a higher research activity. From 2010 to 2015, Marquette nearly doubled their research expenditures, and they have goals to essentially double again. So they'd like to become a $50 million research institution, and we're being led by the president of the university, who his name is Michael Lovell. He's actually on the mechanical engineering faculty. So it's actually nice to have someone sort of steering the ship that comes from our college and understands the value of engineering research. And so the university has put in some offices. They have an Office of Research and Innovation that funds a lot of seed programs within the university. We have formal teaching buyout now, which is really important because it allows faculty to be a lot more involved with their graduate students. And then, as I'm going to talk about today, towards the end of the presentation, we have many TA and RA opportunities if you're interested in graduate school. The other thing I wanted to mention before diving into the topic is that I'm not the only faculty member working on combustion research. So we do feel like we have a growing community of like-minded people within the mechanical engineering department. So we have Professor Somesh Roy, who actually just was granted an NSF Career Award to do soot modeling, which is a very prestigious funding opportunity. So we're really happy for him. He really focuses on sort of fundamentally how soot is formed and modeling that process with computer simulations. We also have Dr. Simka Singer, who focuses on modeling fuel evaporation. And then myself personally, I focus on engine research. So I do a lot of simulations of engines. I do a lot of engine experiments, both single and multi-cylinder engine. And then I also collaborate with Dr. Casey Allen on our optical rapid compression machine, which is more of a sort of a fundamental reactor where we can study combustion chemistry. And so I think we have, you know, sort of a critical mass now and are really excited about growing and doing work in the combustion research area. And we have folks working on things from very fundamental model development to the application of combustion in reciprocating engines. So diving into the topic at hand, like any good engineer, we have to define the problem first. So why am I talking to you today? What problem am I trying to solve? So the transportation industry in the United States consumes about 28 quadrillion BTUs of energy each year. So this includes all energy used in transportation. So fossil fuels like gasoline and diesel fuel are the dominant ones, obviously, but some natural gas, some propane. This includes all biofuels, so mainly ethanol, and then also any electricity, so any electric vehicles. That's a total energy use. But it's difficult to digest what a quadrillion BTU is. So that 28 quadrillion BTUs is equivalent to about 224 billion gallons of gasoline. So it's not to say that it's all gasoline, but that's the energy equivalent. This is about a third of the country's total energy consumption. So if you include buildings and factories and your homes and everything that we consume on an annual basis, transportation is about a third. Of this energy consumption today, about 90% of it does come from fossil fuels, namely gasoline and diesel. So that leads to the problem statement. The problem is that passenger and commercial vehicles consume a very large amount of a primarily non-renewable resource, fossil fuels, and they emit toxic and greenhouse gas emissions. So this is not sustainable because the resource is not renewable. And then it's also a problem because the emissions negatively impact our environment. So that's the problem we're trying to solve. The negative impacts on the environment are kind of twofold. There's sort of the toxic criteria pollutants that tend to affect local air quality. So these are things like nitric oxides, sometimes referred to as NOx, and unburned hydrocarbons or unburned fuel. So these are a problem because in areas where they become concentrated, like urban settings where there's a lot of vehicles polluting with these emissions, in the presence of sunlight, they form photochemical smog. So in this picture down here, this is a picture of Los Angeles, and in the basin, they have a lot of challenges with photochemical smog, particularly back in the 70s and 80s when vehicles weren't as regulated. Engines also produce carbon monoxide and soot and particulate matter, which are also obviously very damaging to human health. Other emissions that we care about, and this is more recently, right? So this wasn't really on our radar, say 30 or 40 years ago, but greenhouse gas emissions and how they affect global climate change. So when we burn fuels, we release CO2. If you're working with natural gas, you might release some methane. And it's not really a challenge for combustion engines, but some industry applications will emit nitrous oxide. And these are the top 3 greenhouse gases. So when they get trapped up in the upper atmosphere, they have a greenhouse effect that basically catches solar radiation that's trying to escape back out into space. And these gases absorb them and then re-emit them back to the Earth. And so the carbon dioxide, methane, and nitrous oxide concentrations in the atmosphere are increasing, and this leads to a greenhouse effect. So this is essentially a bad thing, and it's certainly due to human activity and combustion. So the second thing that we do as engineers is we define the problem, and then we try and find a solution to the problem. So how are we going to try and solve this problem? So popular media would suggest that we won't have engines in the very near future. It's a completely dead technology. So you probably come across articles like this if you're interested in engines where they say that it's completely dead.
Hey, sweets. Are you still working? Okay, good.
So these claims, I would argue, typically refer to passenger cars. They don't really say it that well in the articles. And I would also argue that these claims are somewhat overstated. So I do believe that battery electric vehicles will be a very important technology for the future of sustainable, clean transportation. I think they're a great thing. I think we need to be a little more honest about what sectors of transportation are well suited for battery electric vehicles. So I want to be very clear, I am not anti-electrification, I'm pro-arithmetic, right? So I don't bash technologies, we just do the math and then we decide if it's a good technology. So let's do a little bit of analysis in this presentation to kind of walk through what sectors might be good for electrification and what sectors might we still need engines. So why would anybody consider to keep developing the internal combustion engine? Well, we're talking about transportation. So from a systems engineering viewpoint, this is a mobile application and we have to carry our energy source on board the vehicle. So energy density is of the highest priority. And the rolling resistance of a vehicle scales with its mass because of friction, and the aerodynamic drag of the vehicle scales with its volume because of the frontal area. So if I'm carrying around an energy source that propels my vehicle, I want to be energy dense on both of these fronts. I want to be energy dense on a mass basis and a volume basis. So here are a bunch of energy carriers. And it's a scatter plot of the mass-based energy density versus the volume-based energy density. So I want to be in the upper right-hand corner, which is energy dense on both fronts, and that's where we find fossil fuels, okay? So that's gasoline and diesel are very dense in terms of how much energy they carry per unit volume and per unit mass. A lot of times people talk about hydrogen fuel cells as a propulsion mechanism for vehicles, and hydrogen has a lot of challenges from a production standpoint, but it also has a lot of challenges from a storage standpoint. So hydrogen gas at standard pressure and temperature has essentially no volume-based energy density. And if you compress it to 700 bar, which is very high pressure and requires a lot of energy, you can start to get some volume-based energy density, but it's not very good. And if you liquefy it, which is very hard to do, obviously cryogenically, and then store it as a liquid is very challenging, you're still have very low volume-based energy density. In the way down lower left-hand corner is where you find the lithium-ion battery, which is the energy storage device in a battery electric vehicle. So it has very, very low energy density on both a volume and a mass basis. So just to give you some context here, if you take sort of the extremes like a Airbus A320, it carries 266 megawatt hours of fuel energy when it's fully loaded with fuel. If you used a state-of-the-art lithium-ion battery to replace that fuel tank and have a 266 megawatt hour battery, the battery itself would be 19 times the max takeoff weight of the airplane. and it would take 11 days to charge the battery. So a full battery electric airplane is kind of a non-starter with current technology. Bringing it back down to earth in an application that I'm very interested in, if you just look at heavy duty trucks, so a class 8 semi truck that has a gross vehicle weight of 80,000 pounds, if you wanted to have a 500-mile range battery electric version of that truck, you would need a 1,000 kilowatt hour battery pack. That battery pack would weigh about 15,000 pounds, and that's lost payload for the operator of the truck. So that's a bad thing. The battery itself would weigh about $180,000, which at current battery prices, which are coming down admittedly, but that's really expensive. And that's about the same price that the diesel truck costs today. That's just for the battery. And even with a state-of-the-art charger, you would have to charge this thing overnight for about 12 hours. So my main message here is that it's really important to keep in mind that hydrogen and batteries are simply energy carriers, and they're actually pretty bad energy carriers because they're not very energy dense. In addition to that, you really have to do the analysis on a life cycle greenhouse gas basis, meaning hydrogen is not naturally occurring. We have to make it. And you usually have greenhouse gas emissions associated with making that. Batteries are also not naturally occurring, and there's a lot of CO2 emissions associated with battery production, and they also use a lot of rare earth metals that have a finite supply. So when you talk about driving a battery electric vehicle and saying that we're using, renewable resources, that's not necessarily true. There's a lot of non-renewable resources in the battery. So you just have to keep these things in mind. So I think I've made it pretty clear that liquid hydrocarbon fuels have sort of unrivaled energy density, which is sort of repeated in this plot here. This is just the energy density of fuel, hydrocarbon fuels versus a lithium-ion battery. But conversion also matters. So if you look at the power density in kilowatts per kilogram of an internal combustion engine versus an electric motor, the electric motor is more power dense. So you have to kind of take a little bit of a deeper look, and for different applications that have different power requirements and time of operation requirements, that will likely determine the optimal system. And it's not really a slam dunk that the battery electric vehicle could be used to replace all internal combustion engines. So why don't we combine this picture and look at a couple of different applications? Before we do that, I want to remind you that there's another important aspect here, and that's recharging time or filling time. So in some applications, filling time is maybe not important, but in some applications, it's really important. And so for liquid fuels, I think you can all appreciate that filling up your car doesn't take very long, right? And so the reason for that is that the energy flow in a fuel nozzle is just astronomical. Most commercial gasoline nozzles for passenger car vehicles run at a flow rate of about 5 gallons per minute. That means that there's 10 megawatts of power flowing through your hand. And if you're filling up your heavy duty diesel truck at a truck stop, they tend to have higher fuel rates at about 30 gallons per minute. And that's a power of about 60 megawatts. If you compare that to charging an electric vehicle, if you were to charge it with what's known as a level 1 charger, which is the power coming out of your wall, like in a residential home with a 20 amp service on that particular outlet, you're only flowing about 2 kilowatts. You can upgrade to a 240 volt 80 amp service, which is known as a level 2 charger, and these are definitely available today when you purchase an electric vehicle, but that's still only 19 kilowatts. And even a Tesla supercharger, which is a level 3 charger, which is 480 volts and 300 amps, that's only 144 kilowatts. So why don't we do some very simple analysis where we can evaluate for different applications the trade-off between charging time and weight and all these different factors, and see if an internal combustion engine or a battery electric vehicle is probably a better solution. So this is some analysis that was actually done by a colleague of mine at the University of Wisconsin. His name is Sage Kochon, and we've sort of co-authored a few papers together, sort of comparing alternative fuel IC engines to battery electric vehicles, and he was kind enough to share these couple of slides with me. So, but I think it's very enlightening. So if we look at Sage's analysis, this is a plot that we're going to look at. So I want to explain it before we look at it, where it's power of the propulsion system versus operating time. And then what's being plotted on the contours is the mass of the electric vehicle minus the mass of the internal combustion engine system. And so if you want to operate for longer periods of time at higher power levels of the BEV, you're going to need a bigger battery, and it's going to weigh more compared to the engine. So that's why this contour plot looks like this. We're going to look at various applications, and here are some of the assumptions that we're going to assume for the battery electric vehicle and the internal combustion engine. So we're going to size the application for peak power, because you're going to have to hit certain power levels, even though on average you're going to have much less power. The internal combustion engine will assume an efficiency of 35%, which is pretty reasonable. The BEV will have a charging efficiency of 85%, which is pretty reasonable. And we'll take sort of a state-of-the-art energy density for a battery, which is about 250 watt-hours per kilogram. So the first application I want to look at is what I would call just a light-duty passenger car. So this wouldn't be like the sports car Tesla. This would be, you know, a battery electric vehicle bought for commuting. It's not really a high power application. It has a peak power of only 100 kilowatts and an average power of about 20 kilowatts. And it has a 3-hour operating time. So this would have a range of maybe a couple hundred miles, but certainly not a range of say 400 or 500 miles. That's some of the really expensive, really high power output Teslas and other vehicles that are being advertised. So if we said we needed a battery that would give us 3 hours of operation and 100 kilowatts of peak power, then the battery and the motor together would weigh this much, and the fuel and the engine would weigh this much, which is a difference of several hundred kilograms. The other factor here is, how can I refill my vehicle? So if it's the IC engine version, you can fill it in almost no time. If it's the battery electric vehicle, it's going to be really challenging to charge this overnight so you can go to work every day with your standard outlet in your garage today. But you could very easily upgrade to the level 2 charger, and you'll be able to charge this vehicle overnight, no problem. You could drive this vehicle to work every single day on a full charge. And even if you wanted to drive from Milwaukee to Platteville and drive around for the day, and you couldn't quite make it back to Platteville or Milwaukee, if you could find a Tesla supercharger somewhere in the area, you could charge while you're having a meal. It would only take a half hour and you could drive home. So this is a great application for battery electrics, right? You don't see a lot of challenges with changing the consumer's way of life. And the extra weight is probably not a factor because you're not carrying any payload. The vehicle is just going to weigh a little more. I think the only challenge is if the electricity can be made cleanly, then this is a great application for battery electrics. The challenge comes in as we start to get to bigger and bigger vehicles. So if we look at like a medium duty application where this is more of a commercial vehicle application. This could be a pickup truck towing a trailer. This could be a large cargo van full of tools, but it's a vehicle that the operator is using for his way of life, and he's got some payload. So it's a bigger vehicle, it has higher power. We need to size the battery to run all day long, because if you're towing trailers back and forth to the work site, or maybe it's a small dump truck hauling, you know, aggregate, it might run all day long. And so we're going to size the battery for 8 hours, and it's going to be a big enough battery to deliver these types of power levels. And that means compared to a gasoline or a diesel engine, it's going to weigh about 2,000 kilograms more, which is, you know, roughly 5,000 pounds or something. So it's a significant amount of weight that we're going to have to carry around, and that might negatively affect your cargo or your payload. The other challenge with this is charging, right? So if you charge this medium duty vehicle at your garage or your shop or your place of business overnight, even a level 2 charger is not going to charge it overnight. So if you need this vehicle every day and you used it for 8 hours one day, you won't be able to use it the next day with a level 2 charger. And you might be able to get a supercharger in your home, but I don't know if that's the case today. And you could charge it in 4 hours, but you would need a supercharger. You'd need a level 3 charger. So I think this is a challenging application for BEVs due to the weight and the current charging capability. Not to mention the electricity would still have to be made very cleanly. Continuing with that theme, if we were to look at a Class 8 semi-truck where we would need average power of over 100 kilowatts and peak power of 600 kilowatts and operating times of at least one driver shift, which legally can be up to 11 hours, but a lot of times they drive in teams where they don't have to stop at all. They can drive 24 hours a day because they just go on and off shifts. But even if it was only one driver for 11 hours, you would need to size the battery to drive for 11 hours, which would be 6,000 kilograms heavier than the engine. And that's where that 15,000 pound number comes from. That's how much the battery would weigh. So you're giving up a lot of payload, which is not good for commercial transportation. That's what you're hauling is payload. And also, when they do stop to charge, it's just not really feasible to charge a battery of this size for as long as they want to stop. They might only stop for a couple hours if it's a team driving, or even if it's a single person driving, he would need 12 hours to charge this vehicle. So in my personal opinion, this is a very challenging and not likely application for battery electrics. And if we want to solve our problem, we're going to have to go a different way. So if you look at some projections, you can see some of these themes. So this is projections out to 2040 for transportation energy demand. And so you see gasoline, you see diesel fuel, you see jet fuel for aviation, you see natural gas, and you see electricity. So electricity is starting to grow because BEVs are certainly going to penetrate the light duty market. And that's why gasoline demand is going down around the world. Diesel fuel demand, however, is projected to grow by about 40% in the next 20 years. This is due to the developing world and the growing global economy and e-commerce and things like this. You know, the economy is driven by heavy duty trucks, large ocean going vessels, rail, all those things. So as the economy grows, diesel engine demand grows. It's very difficult, as I just said, to fully electrify these sectors. So these sectors are growing due to the growing world and the growing economy, and they're sectors that we can't really electrify. So the problem is getting worse and worse and worse because we're burning more and more diesel fuel in the coming decades. So there's an imminent need to decarbonize heavy-duty diesel engines, and we need to do it with renewable, low life cycle greenhouse gas fuels because battery electrics are not a good technology for this sector. So when I say low carbon alternative fuels, what am I talking about? Well, there's a handful of candidates. There's more than what I'm going to list here, but these are the ones that I'm interested in. So the alcohols, say methanol and ethanol, maybe even butanol and propanol, they can be made from a variety of biomass feedstocks, among other things, and they will have, roughly 30 to 60% lower life cycle carbon because they were made from a feedstock that absorbed CO2 when it was growing, hence the term biofuel. Natural gas and propane are fossil fuels, but they have lower indigenous carbon compared to gasoline and diesel. So using them as fuels in the near term is a good way to curb our CO2 emissions because they will emit less CO2 per unit energy. And then hydrogen and ammonia, are interesting fuels because they're carbon free. They have some challenges with energy density, like I talked about before. But if you can make them from renewable energy, and then they're truly carbon free, these are very interesting energy carriers for engines as well. The problem is all of these fuels are very difficult to auto-ignite. So they make very good spark ignition engine fuels, but they make poor diesel fuels. And I'm proposing that we replace diesel fuel with these fuels. So I think the obvious answer is, why don't we just use spark ignition engines in the heavy duty sector? So why don't we just use an SI engine in a semi truck? Well, there's a reason that you don't see that today. It's because SI engines, they can't meet the performance demands of a heavy duty application. So if you look at the torque curve of an engine, SI engines have challenges with premature auto ignition at high torque levels. At high power levels, they have to do fuel enrichment to protect the components from high temperatures. And they also have really poor efficiency at part load. So the SI engine is really just not well suited for the heavy duty sector. They just can't really deliver the performance in terms of efficiency and peak torque output that a diesel engine can. So the challenge is, I want to burn fuels in a diesel engine, but they're really poor diesel fuels. So before we press on, I think it's really important that we know, what does the diesel combustion process look like, so that you know what we're trying to reproduce. So this is a CFD simulation of a diesel engine showing what the diesel combustion process looks like. So you can see here in the animation, it's a double injection strategy where we have these two injections shown in blue. And then the chemical energy release, or the burn rate of the diesel fuel, is shown here in red. So because the diesel fuel ignites pretty quickly, we can establish what's known as a non-premixed mixing controlled combustion process, where the fuel in the air can only react and release energy when they find each other. So the burn rate is limited by mixing, hence the term mixing controlled combustion. And this combustion process allows us to run really high torque output because we don't have any premixed fuel, so we don't fear premature auto ignition. And it also has a lot of other characteristics that are desirable for heavy duty engines. So this is the combustion process that we want to reproduce, but with alternative fuels that really don't want to auto ignite. So let's quantify, like, how big is this problem, right? How hard are these fuels to auto ignite? So this is a plot of ignition delay versus temperature. So it's the inverse of temperature. So low temperatures are shown over here, and then higher temperatures are shown over here. And so you can see the ignition delay is on a log scale. So it's very important that we're traversing very different amounts of time here. And then we have a bunch of fuels shown on this plot. So if we look, diesel fuels are low octane, meaning they have a short ignition delay. They auto ignite very readily. These are things like diesel fuel, which is not shown on the figure, but N-heptane and dimethyl ether, they have the reactivity, if you will, like diesel fuel. So N-heptane and dimethyl ether, in the temperature range of interest for engines, which is, you know, between 700 and about 1200 Kelvin, we see ignition delays that are relatively short, you know, on the order of a millisecond or less. And that's what allows you to establish that mixing controlled combustion process pretty quickly. Things that are poor diesel fuels, here I'm using methane as an example, but the alcohols, propane, hydrogen, they all have relatively long ignition delays, kind of like methane. And so in this temperature range of interest, we're up here in the 10 to 100 to 1000 millisecond auto ignition delay time for methane. So those are very high octane, very hard to ignite fuels. Well, you might be thinking, well, 10 milliseconds, I mean, 10 milliseconds isn't a very long time. So why do we care if the ignition delay is 10 milliseconds longer for methane than N-heptane or something? Well, in an engine, 10 milliseconds is forever. It's an eternity. The piston goes from top dead center to bottom dead center in 180 crank angles. So 10 milliseconds is 120 crank angles. So it's almost the entire expansion stroke. So if you had an ignition delay of 10 milliseconds, the engine wouldn't run. You'd have no combustion with these higher octane fuels. So we need an ignition assistance device. We need to somehow rapidly ignite a fuel that doesn't want to ignite, such that we can establish the mixing controlled combustion process and make a diesel engine run like a diesel engine, but on a fuel that doesn't want to auto ignite. So let me illustrate that a little more clearly with the most simple way that I can think to do ignition assistance. So you can see that ignition delay time is very sensitive to temperature. So all we got to do is get it hotter. If we can get the methane hot enough, it will have the ignition delay very similar to a diesel fuel. So if we look here, this is the energy release rate versus crank angle. And the black line shows a conventional diesel engine where we inject the fuel close to top dead center, and we only have to wait, a couple of tenths of a millisecond, and then ignites. And then we have an energy release rate that's a very mixing controlled combustion process. Now, if I was to substitute that fuel with ethanol, which is very hard to ignite, the engine would totally misfire. Unless I take this very normal intake temperature and increase it to a little over 100 Celsius, then the engine would finally actually fire, but the combustion would be very late, it would be very unstable, and it would be a very poor running engine. If we wanted the ethanol to mimic the diesel combustion process exactly, we would have to run an intake temperature of 160 C, which is about 100 degrees hotter than a normal engine operating condition. Where you're going to get this heat from is, unknown. You could run a heater or something like this, but this is obviously going to hurt the engine efficiency. And it's also very difficult to control intake temperature very rapidly. So intake temperature control is kind of a difficult thing, but this kind of illustrates that if we could heat the engine enough, we could run the engine on something like ethanol. What we're working on is something that we think is obviously a little more innovative, but is something that we can control on a cycle-by-cycle basis. So what we're trying to do is develop an actively fueled pre-chamber, which will serve as an ignition device. So a diesel engine would typically just have this center direct injector delivering these blue plumes, which would be the diesel fuel. But then we have this pre-chamber igniter where we can have a separate fuel injector filling that pre-chamber. We can fire a spark plug, and then hot jet flames will emanate from the pre-chamber. And then when we direct inject a fuel that doesn't want to ignite, if it comes in contact with an already burning flame, it will auto ignite. And so the pre-chamber jets serve as our ignition source. We've been able to show with simulations, this will allow us to run all sorts of different high octane fuels that don't want to auto ignite, such as gasoline and ethanol, natural gas, hydrogen. And you could even run blends of those fuels, because if you have an ignition assistance device that is robust like a flame, octane number doesn't really matter anymore. Anything that comes in contact with the pre-chamber jet is going to ignite. And so you could even think about having a heavy duty vehicle that's sort of a flex fuel vehicle that could run on gasoline ethanol blends. It could run on natural gas, propane, hydrogen blends, or anything that you can think of. Let me just illustrate quickly that we're able to reproduce the diesel engine process. So here's a diesel engine doing in-cylinder CFD simulation, so modeling the spray and combustion process. And you can see that we direct inject the fuel at 5 degrees before top dead center. And the diesel engine gives us that classic diesel engine burn rate. And you can see the cylinder pressure as well. Well, if we just take that same engine and put our active pre-chamber on it, and keep the direct injector, and then change the fuel to ethanol, we can keep the intake temperature the same, which if you were to just direct inject the ethanol at this intake temperature, the engine would totally misfire. But you can see here, if we fire the pre-chamber at 10 degrees before, which is before the direct injection, we can have hot jet flames coming out of the pre-chamber right before we direct inject ethanol. And the direct injected ethanol sort of chases that flame, and once it hits it, it ignites. And then you can see that we can reproduce the diesel combustion process with ethanol, and this engine will have very similar efficiency, very similar torque characteristics, and all the things that we love about a diesel engine, but running on pure ethanol. I think in the interest of time, I'm going to just gloss over this really quickly. But basically, the thing that we really like about the pre-chamber is that it's very robust. Meaning, if you look at the start of combustion versus changing the intake temperature, it's very, very flat. Meaning, we don't want the engine to be sensitive to intake conditions. It's desirable for it not to be sensitive, meaning if it's cold outside or if it's hot outside, the engine runs the same. Where if you don't have a pre-chamber and you're relying on intake temperature to be your ignition assistance device, even if you can get really high intake temperatures, which is hard to do, you'll be still quite sensitive to whatever that temperature is. So the engine might be sort of unstable if you're counting on intake temperature to be your ignition assistance device, which is not desirable. I think the last piece of the puzzle that I want to sort of discuss here is the main mission here was to solve the problem of using large amounts of non-renewable fuel and the impact on global climate change. So we want to reduce our CO2 emissions. Well, if we can reproduce the diesel combustion process with diesel engine efficiency, the whole story here then is just give me a fuel that has the lowest life cycle CO2, meaning it has low CO2 in its production, and we can reduce CO2 emissions dramatically. So here you can see if we could take a diesel engine and run it on blends of ethanol all the way up to pure ethanol, we could cut greenhouse gas emissions by about 50%. And this would be from ethanol made from corn in this country, or ethanol made from sugarcane in Brazil, all these different sources. They all have slightly different life cycle CO2, obviously, but because of improved farming practices and distillers grain and things like this, every year these numbers are getting better and better. As a point of discussion though, even though the battery electric vehicle semi, I think, is sort of impractical from a weight and charging perspective, it's also not that great from a CO2 perspective. Meaning if you're charging from the US electricity grid, which has brake-specific CO2 emissions of only 400 grams per kilowatt hour. So the power plants are a lot better than a diesel engine from a CO2 perspective. If you include the transmission losses and the charging efficiency of the battery, the discharging efficiency of the battery, and the electric motor efficiency, the battery electric semi would have CO2 emissions of 640 grams per kilowatt hour. So it would be a little bit better than the diesel engine. It would be a little bit better than the engine running on a blend of 15% ethanol and the rest gasoline. But all these other ethanol blends, and certainly pure ethanol, are much better from a greenhouse gas perspective than a full battery electric truck. And the battery electric truck has all those practical challenges too. So I wanted to let you know that we're really excited about this concept, and we have two federally funded projects working in this area. The one talking about ethanol is being funded by the United States Department of Energy, their Energy Efficiency and Renewable Energy Office. Marquette is leading this program, which is supposed to start next month. And we're partnering with the University of Wisconsin, John Deere, Clear Flame Engines out of Chicago, and Mala Powertrain out of the Detroit area. And so we're all going to be working together to basically demonstrate this technology. We have another project that's funded by ARPA-E, which stands for the Advanced Research Projects Agency Energy, who I will tell you right now is the best institution at coming up with acronyms. If you ever need a good acronym, pay them to do it, it'll be worth it. So they had a project or a program called REMEDY, which stands for Reducing Emissions of Methane Every Day of the Year, because methane is a very powerful greenhouse gas. And so there's a lot of engines in the natural gas pipeline industry that run on natural gas, and they emit a lot of methane. And it's because they're premix charge SI engines that have a lot of incomplete combustion. If we could convert those engines to this concept, we've been able to demonstrate that you'll have very little methane emissions. And so we think that we can convert natural gas engines to operate with this concept, and we will reduce methane emissions by a large amount. And so that's another project that's supposed to kick off this summer that again, Marquette is leading, and we're working with Wisconsin and Mala, and also a company out in Colorado known as C0, who develops natural gas fuel injectors. So we're super excited about that project as well. I think last thing is I just wanted to mention that if you're interested in this kind of work or just graduate school in general, the mechanical engineering department has programs for a master's of engineering, certainly a master's of science, and also a doctor of philosophy. And we have research assistantships and teaching assistantships available. So the research assistantships would be if you're working on a project that was, supported by external funding, such as the two I just mentioned. But then we also have plenty of teaching assistantships available where if you weren't really sure what kind of research you wanted to do and you wanted to come to Marquette and start to pursue a graduate degree and maybe pick a faculty advisor later, we will certainly have opportunities to get you started that way. And both the teaching and the research assistantships come with full tuition and a monthly stipend. And so if you're interested, I would just encourage you to apply, and then we can kind of go from there. So I apologize for kind of losing my voice. I'm sort of getting over a cold, so hopefully you could hear me reasonably well. But I just wanted to thank you so much for your attention and coming. My contact information is shown there, and feel free to email me with any questions, or if you want to ask questions now, that's obviously great. And so I'll just leave you with two pictures of our research facilities. So this is the internal combustion engine lab that we're going to be developing this technology on. It's a Caterpillar diesel engine. And then also the rapid compression machine lab, where we do a lot of fundamental fuel chemistry experiments. So anyway, thanks again for your time. And I'd love to just have any questions and discussion.
I have a question. Can you hear me?
Yes, I can.
Okay. So your focus is mostly on like adapting a diesel engine to run on high octane fuels. What would be why is this better than targeting like drop-in biodiesels? Like I know biodiesels exist, but I don't know a lot about them. So why is this a better alternative than utilizing biodiesel or other equivalents alternatives?
Yeah, that's a great question. Actually, that's a really good question. And I need to do a little research myself to try and understand that. Because if we would just use renewable fuels that had low octane or high cetane, we wouldn't need the pre-chamber. And I think the challenge there is that they're just not as low of life cycle greenhouse gases as we would like. Specifically, like synthetic fuels. People talk about renewable gasoline and renewable diesel fuel that might not be made like biodiesel is today from biomass. It might be made from hydrogen and sequestered CO2, and then you upgrade it catalytically to something that looks like gasoline or looks like diesel fuel. And those processes take a lot of energy. So the way that I think about it is like the simplest, what's known as an e-fuel or a solar fuel is methanol. And so if you're going to make hydrogen and CO from sequestered CO2, the first step is methanol, and then you have to upgrade it to synthetic diesel fuel. And that just takes a lot of energy. And my thought is, let's just use the methanol. And so I think that's a very valid question and something that we have to wrestle with as we develop engine technologies. And as the fuel producers that do their research, we want to use the fuels that are the lowest greenhouse gas emissions to get them in the tank, and then we'll find a way to use them. So if the synthetic fuels that have diesel fuel properties are lower life cycle fuels, then we should use those. But I'm just not 100% sure that they are.
Got it. Thank you.
Do you happen to know a lot about that, and do you have any feedback on that?
I don't know about diesel, like synthetic diesel. I know more about synthetic or sustainable aviation fuel and like different production pathways for those. And I know that right now there's a lot of work being done to reduce the life cycle emissions for the actual production processes, like especially like companies like LanzaTech. They now have like LanzaJet, and they're focused on making the actual facility run on renewable energy, like from wind turbines and stuff like that. But I'm not sure about diesel or automotive applications.
Right. Yeah. I think it's all very good questions. I mean, if you could make renewable jet fuel, that's a fuel that's kind of between gasoline and diesel, right? It has a cetane number in the 20s or something. So that would be a fuel that I realize it's being targeted towards gas turbines and aviation. But if it can be made with a lower, life cycle greenhouse gas footprint than anything else, we could use it in reciprocating engines too on the ground, but you might need ignition assistance there. So I think the really short answer to your question is that we want to develop a technology that could be fuel agnostic, right? We would not necessarily need to fire the pre-chamber if you're running on a fuel that didn't need ignition assistance. But if you were running on, say, methanol or ethanol that needed ignition assistance, you could use it. So we want to develop like a fuel flexible platform, because I think the future of fuels is so uncertain right now. Like, what can we make the most sustainable?
Okay. I have a question.
Yes.
Can you? Okay, great. So, I have like several questions actually, but I'll keep it like 3, and then maybe email you later the rest.
Okay.
So, so the first is, I guess the engine you are going to use will not have exhaust gas recirculation, right? And then, secondly, how are the control modifications going to be implemented? Like, will you have to keep the same ECU settings for your concept? And yeah, and like really, how is the pre-chamber going to be, commanded in terms of like control loops and all that? And also, are your consideration of the concept related to the CA50? Because I know that is that CA50 is a great combustion, index for stability and efficiency and all that. And I think it's also relates to the pressurized rates. Are you going to encounter any pressurized rates limits with regards to your concepts and all that? Yeah. Thanks.
Yeah, these are good questions. So I'll take the first ones first. I mean, certainly the engine could have exhaust gas recirculation. In fact, it probably will, because if we reproduce the mix and control combustion process well, we're going to form NOx emissions. So we're probably actually going to run EGR, and how much, remains to be seen. But EGR is a great way to reduce NOx emissions, so we're certainly going to do that. In our engine lab here, I didn't have enough time to really talk about it, but it's a fully flexible platform, meaning it's a single cylinder. Can't really see it in this picture, but we have an EGR loop. So experimentally, I can run any EGR level that I want. In production, this engine may or may not have EGR depending on the customer needs and the emissions regulations of the sector that the engine is being sold in. Your other question was about controls. So again, in a research setting, I have control over everything, right? So we don't run off the Caterpillar ECU. We run off an open access LabVIEW based controller that if I put a new actuator on the engine, such as the fuel injector and the spark plug in the pre-chamber, I can control when this fires and when this fires and when this fires. And those are all very basic automotive controllers. So from a research standpoint, I can do anything. In a production environment, yeah, you'll have to add some channels to the ECU, but that's trivial. And this would be a GDI injector likely, and this is obviously an automotive spark plug. And so, yes, we have to control these 2 additional, I guess what I call actuators, but that's simple to do. The challenge is doing the research to figure out when to fire the pre-chamber injector and when to fire the spark plug.
Exactly. Yeah.
it's my feeling that we won't need any closed loop control over that, meaning we'll sort of do our research and figure out when to fire these things. But in all of our simulation work, firing it a handful of crank angle degrees before you want to do the direct injection gives enough time, because the fuel injector in the pre-chamber is fired much, much earlier. So I kind of skipped over that detail. But during the intake stroke is when I would fire the pre-chamber injector and allow the fuel and air in the pre-chamber to mix. And the pre-chamber should aim to be homogeneous and a nearly stoichiometric mix. And then when you fire the spark plug, you'll have a flame that propagates through the pre-chamber and shoot the jet flames out. So we hope to have a very simple controller based on table lookups. We just have to do the research to figure out when to fire those actuators. Does that answer your question?
Yeah, it does. So in that case, your SOC will be the spark ignition, right? Will you mainly say that that would be a SOC then?
You mean start a combustion?
Yeah.
Yeah, I don't know. That's a good question. I mean, certainly in the experiments, we're going to have a pressure transducer in the pre-chamber, and we're going to have a pressure transducer in the main chamber. So this is CFD modeling, but in our experiments, we'll be able to compute heat release rate in the pre-chamber and heat release rate in the main chamber. So I could tell you SOC, CA50, all that stuff in each chamber. And I realize what you're saying is that those metrics are really tied to efficiency, but we'll be able to put them wherever we want because we have control over this spark plug and the direct injector. So if I move everything to the left, everything shifts to the left. And if we move those actuators to the right, everything shifts to the right. And so we have control over the start of combustion, which is the really important thing.
Okay, got it. Oh, awesome. Yeah, all right, thank you.
Yeah, no problem. Good question.
Do we have any questions from here in-house?
Yeah, hello.
No?
Yeah.
All right, so here, before we continue the discussion, we will continue until, you know, we feel tired. So it's 6 o'clock, so I'm gonna close the seminar for those folks who want to leave, who has to leave. Feel free to leave, you know, and then others, we will continue discussion here, and then Scott will be here as well, and then the speakers, so we'll continue discussion if you have questions. Just want to let you know that don't feel guilty that, you know, you have to sleep out early. So don't worry, it's 6 o'clock. So thank you for attending, and then we'll continue the discussion.
I see one question in the chat that might be a natural kind of segue, and that would be kind of what are the next steps for pre-combustion research? Like where are you at this point kind of going forward?
What are the next steps for like this technology? You said pre-combustion?
I think they mean the pre-chamber combustion, like actually getting it implementable is how I'd interpret it.
Yeah, okay, gotcha. So yeah, you know, both of these projects that I mentioned that are funded by the, you know, federal government, one of the first tasks is to do more detailed CFD modeling where these are very simple CFD models where the pre-chamber injector and the spark plug they're not physically in these models. We assume a homogeneous mixture of fuel and air. We locate a CFD cell in the pre-chamber and dump a lot of energy to it, and that initiates a propagating flame. What we really need to do is take a step back and include all of this geometry. And so that's our first task, because we're going to spend probably the first 6 months building a CFD model that includes the cylinder head, the valves, all this detail. And we're going to model the spray inside the pre-chamber, model the spark ignition process. And what we need to do is optimize the volume of the pre-chamber. We need to optimize the passageways. You know, these passageways are like anywhere between 1 millimeter to 2 millimeters in diameter. And there's a trade-off between passageway size and the ability to build pressure in the pre-chamber. So the pre-chamber pressure goes up due to combustion, and that's what shoots the jets out. Well, if the holes are too big, you can't build up any pressure. And so we really need to do an optimization of the pre-chamber's geometry in terms of volume and passageway size. And then we need to do a design exercise to find room for this in the engine. And so that's where like John Deere and Mala are going to help us out. They have a lot of design experience for 4-stroke, 4-valve diesel engines, and they're going to help us find room for the pre-chamber. So hopefully that answers the question. Is basically designing the thing and then finding a way to implement it is kind of the first step.